Hello, AP Chemers. Our topic is the relationship between molecular structure and acid-base properties. For short, it's really talking about how do you know if there is an acid and what determines the acid's strength. So many substances contain hydrogen, but not all substances that have hydrogens in them are considered acidic. For example, natural gas, which is methane, CH4, is not really considered an acid. In fact, it's almost neutral. So why is that? Well, the reason is for a substance to be an acid, according to Bronsted-Lowry, it has to give off an H+, which means that bond between the hydrogen and whatever atom is in the rest of the molecule needs to break in order to give off the H+, and the A-, the electrons, move from that bond to the A to form A-, and then H+ leaves. And so CH4 does not produce H+, and therefore it's not considered an acid. And the reason for that is because that CH bond is very strong, that it's very hard to break and very hard for those electrons to go on the carbon, leaving the H+ behind. So what determines the strength of the acid, or how much that acid will dissociate to give off H+, because that's what the strength of the acid is? Well, two factors. The first factor is the strength of the HA bond, which goes together with the polarity of the HA bond. So the polarity of the HA bond causes the bond to be either strong or weak. So let's think about this. If it's a strong acid, what does that mean about the HA bond? Well, that means that the H+ can leave readily, which means that that bond can break readily, which means that that bond is relatively weak. So let's write that down. So weak HA bond corresponds to stronger acid. Now, the strength of the HA bond depends on its polarity. So if you think about it, let's look at the series of the hydrogen halides here. So we have HF, HCl, HBr, HI. From your previous knowledge about these, 3 of those 4 are strong acids, but one of them is weak. Do you remember which one? So it turns out that this one is weak, but the rest of them are strong. And if you had to guess, if you know that HF is the weakest, you would probably guess that the HI is the strongest of those acids. Now let's think about why. Well, based on what we just said, the HF bond is would be the strongest bond. According to that. That means that H is really hard to leave, or H+ is really hard to leave. The bond is strong. We can't break it very easily. The HI bond would be the weakest bond, meaning that those electrons can go to the iodine, leaving the H+ to be removed. Well, why is that? If you look at the electronegativity of hydrogen versus fluorine, and then hydrogen versus chlorine, hydrogen versus bromine, and hydrogen versus iodine, you will see that the electronegativity difference between hydrogen and fluorine is the largest, and it's the smallest for the HI. This is the most polar HA bond, I guess. You could call it that. This is the least polar HA bond. And again, A would be your iodine or your fluorine or chlorine or bromine or whatever. So that means that you have a partial positive and a partial negative in that molecule. The hydrogen has the partial positive. The iodine here has a partial negative. Here, the hydrogen has a much larger partial positive, and the fluorine has a much larger partial negative, which tells you that hydrogen and fluorine are really attracted to each other because of the large partial positive and negative. So it is hard to break that bond. That bond is really strong between them. Whereas here, yeah, they're attracted, but not as attracted as the HF bond, and so this bond is easier to break. It's a weaker bond. And so the less polar the bond, the weaker it is, and the easier it is for the H plus to leave. So let's write that down next to polarity of the bond. The less polar HA bond corresponds to a stronger acid. Okay. The second factor that affects the strength of an acid is the stability of the anion. The anion is your A minus here. So once that bond breaks, the electrons go to the A. So if that ion, or if that part of the molecule can handle that negative charge well, it's stable, then that means that's going to be a stronger acid. If it's not okay with that minus there, it can't handle it, it's not very stable, it's going to react again with the H plus to reform HA. So the more stable the anion, the stronger the acid. So the more stable A minus is, the stronger the acid. Again, because if A minus is stable, then this is going to stay. The products are going to stay. But if A minus is not very stable, then it's going to recombine with the H plus to reform your acid, and there's not going to be as much dissociation. So let's take a look at an example. Let's go back and look at our acid halides here. So F minus, compare that to I minus. F minus is less stable than I minus. Let's write that down. F minus is less stable. I minus is more stable. Why is that? Well, there are many factors that affect the stability of the anion. Nature in general does not like the concentration of anything. It does not like the concentration of pressure or the concentration of particles or anything like that. That's why it always goes from high to low pressure, high to low concentration, high to low energy, and so on. So same thing with charge or electrons. That negative charge, that I minus or F minus, that negative charge means there's electrons. Nature does not like those electrons to be concentrated in one small tiny area. So the smaller the anion, the less stable it is. The larger the anion, the more stable it is, because that negative, those extra electrons, can be distributed over a whole big large iodine atom compared to a very small fluoride ion. Let's look at another example. So here we have HClO versus HClO2 versus HClO3, and then finally HClO4. So we have HClO, and then we keep adding more oxygens and more oxygens and more oxygens. Now, from your experience, you know that HClO4 is a strong acid, and you know that these are going to be weak because they're not from the 6 strong ones. Now, let's actually add the electron pairs real quick, because otherwise, those structures would not be correct. So I need a lone pair on all of these. All right, perfect. So now we can actually look at the structures. And so we know that out of these, this is the strongest of those acids. And this one is the weakest acid. Now, let's start with the bond polarity and the strength of that bond. The number one reason why, acids are strong or weak. So let's compare them. Well, so here's your HA bond. It's an OH bond. Here, an OH bond. OH bond. OH bond. They're all the same polarity. They're all the same strength of bond. For now. That's kind of a simplification, but for this year, we're going to say, since it's an OH bond, OH single bond for all of them, it's the same. So then you look at the stability of the anion. And so according to what we just talked about, that this would be the weakest, that tells you that this is the least stable anion, whereas this one is the most stable anion. Least stable. I'm going to just call it A minus for the anion. And this is the most stable anion. The reason for that is the size, of course, but also, more importantly, something called the inductive effect. So let's define what inductive effect is. So inductive effect is the attraction of electrons from adjacent atoms by more electronegative atoms. Okay. Basically, if you have oxyacids, the more oxygens, the more that inductive effect, the stronger the acid. So let's look back at our acids here. So this anion, OCl minus, this is OCl2 minus, OCl3 minus, OCl4 minus. That negative charge, again, are an extra pair of electrons. And so here, that negative charge, once that H plus leaves, is on that oxygen, but it's also distributed to that chlorine, because that chlorine is very electronegative, so it's going to pull those electrons from the oxygen, so the electrons are going to be distributed over these two atoms. Now look here. The negative charge is there. Both oxygen and chlorine are very electronegative, and so both of them will be pulling those extra electrons towards them. So now that negative charge will be distributed over all three of those. Let's look here. The negative charge on that oxygen, once the hydrogen leaves, is going to be now distributed all over all of these four atoms, because all four of them are very electronegative, so they're going to attract those electrons. And then here, that negative charge, once the H plus leaves, is going to be distributed over 5 electronegative atoms that are all attracting those electrons. And so that charge is going to be distributed over more atoms, more area, and so that is a good thing, because that makes your anion more stable and therefore your acid stronger. So to review, the first thing you look at is the strength of your HA bond first. That's what you consider first. The one with the weaker bond, the weaker HA bond, is going to be the stronger acid. If they all have the same type of HA bond, like they're all HO or they're all S or something like that, they're all the same type of hydrogen to whatever atom bond, then the second thing you look at is the stability of the anion, and that has to do with mainly the inductive effect and partially with the size as well. So let's do more examples. Let's start with H2O versus H2E. What do you think? Which one would be stronger? Well, if you were to draw these, or, even if you don't draw them, you can kind of tell that in H2O, the bond will be between hydrogen and oxygen, whereas here, the bond will be between hydrogen and tellurium. So you can look at the strength of the bond here. And so the electronegativity difference between hydrogen and tellurium is much less, and so this is a less polar bond and therefore a weaker bond, and therefore that H plus can leave, and that's a stronger acid. So this is a stronger acid because the HA bond, or if you want to call it the H tellurium bond, let's do that actually. HTE bond is less polar than the HO bond. Therefore, the HTE bond is weaker, easier to break, and so H2TE is a stronger acid. Okay, let's look at the next one. We have H3ASO3 versus H3ASO4. Now, if you look at both of these, it's the same type of HA bond, right? And so it's actually connected to the oxygen, not to the arsenic there. But either way, it's the same type of HA bond. And so now you look at the stability of the anion, and the one with more electronegative atoms can attract those extra charge or extra electrons towards them via the inductive effect. And so the more oxygens, the stronger the acid. And so in this case, that one, H3ASO4, would be the stronger acid because of the inductive effect. More oxygens, therefore more inductive effect, therefore the anion is more stable. Okay, let's look at the next one. We have CH3COH versus CF3COH. So both of these, it's the same HA bond. So both of these kind of look like this. You have your, I'm going to draw it here. You have your acetyl bond O and then an OH. That's your acidic hydrogen that leaves. And then there's a carbon here. And those three bonds here, those three atoms, are going to be either hydrogens in this case or fluorines in this case. So it's the same type of bond. So you can't really compare the type of bond. What you want to compare now is the strength of the, or the stability of the anion. And so we're comparing fluorines here versus hydrogens. Well, if you have fluorines, fluorines are very electronegative. They're going to pull the negative charge that you would have if that hydrogen were to leave. Now you'd have a negative charge on that oxygen. And so that negative charge can be distributed over the fluorines that if they were here, but not over the hydrogens, because the hydrogens are not very electronegative. And so that tells you that definitely this acid is stronger. You can say the reason is because more electronegative atoms, so therefore more inductive effect, and so therefore the anion is more stable. Okay, last one, HOCl or HOBr. So let's see, let's compare the bond first. So HOCl would look like this. HOBr would look like this. You have lone pairs here as well. All right, so looks like same type of bond, OH and OH. So now what do you compare? Now you compare the stability of the anion. And so because chlorine is more electronegative, and so therefore it can pull the charge from the oxygen once the hydrogen leaves. And so this would be a more stable anion. So the answer would be HOCl. That's it for acid strength.